Prove or disprove. If A and B are symmetric matrices, then so as their multiplication. First of all, remind yourself of the definition of symmetric matrix. A matrix is called symmetric if it's equal to its transpose. A symmetric matrix if A is equal to its transpose. Well, I'm going to give you a counterexample here. We disprove this statement by providing a counterexample. What I'm going to do, I'm going to take two matrices that are simple in size. Let A be matrix 1, 1, 1, and 0. And the second matrix, let B, is equal to matrix 0, 1, 1, and 0. Both of these matrices are symmetric matrices. Why is that? Because the transpose of matrix A, by switching its rows and columns, we get 1, 1. So this is your very first row. 1, 1 now becomes the first column. And the second row, which is 1 and 0, is now become 1 and 0, the second column of your matrix. So what's happening here? We see that matrix A is a symmetric matrix. It is equal to its transpose, no doubt there. So A is equal to A transpose, or it is symmetric. What about matrix B? The same argument. The first row is 0 and 1. So when you're finding the transpose of this matrix, it becomes 0 and 1. And then the second row, which is 1 and 0, becomes the second column of your matrix, which is 1 and 0. So basically, matrix B is also a symmetric matrix because it is equal to its transpose. Now what I'm going to do, I'm going to form their multiplication, their product. Now, let us check the product or multiplication of A and B. The multiplication of A and B, 1, 1, 1, 0 by 0, 1, 1, and 0 is equal to, well, we're going to take the very first row and find the dot product with the first column, which gives us nothing but 1. So here you have 1. Then you're going to take the first row and find the dot product with the second column. You get 1 again. Repeat this process for the second row. The dot product between the second row and the first column gives you 0. And let me use a different color. The dot product between the second row and the second column gives you 1. Well, let's check this matrix. This is A times B. Is AB a symmetric matrix? It means that is AB transpose is equal to AB itself? Well, the transpose of AB is equal to, so the same process as we did before. We take the very first row and we set it as the first column. which is going to be 1 and 1. The second row becomes your second column, 0 and 1. But obviously, comparing these two matrices, they are not equal to each other. So what is our conclusion? Our conclusion is the statement is not true all the time. So the statement is not true all the time because we found a counterexample. Let us recap what we did. The statement was if A and B are symmetric matrices, then so is their multiplication. Remind yourself of definition of symmetric matrix. A is called a symmetric matrix if it is equal to its transpose. We can find two matrices like A and B that when you multiply them together, their multiplication is not transpose, even though it's not symmetric, even though they both are symmetric matrices and they are both equal to their transpose. So this is an example of using counterexample to disprove a statement.